You okay still? What the heck? The system put us together here. We have to make the best of it, right? We need one more thing. So, Georgi, I move to the next one. The last summary statistics that I will be talking about today, as some of the basic ones. This takes us a step further, and we will get back to this situation later in the course. Now, today I'm just talking about looking at the numbers, actually. Then, after we've had a bit of probability theory, we'll get back to doing this real statistics that I promised you. Here's just a way to look at a combination of two observations on persons. And a way, I believe, that we have also tried all the way back to elementary school, I'm sure, that what if I have a number of persons, in this case person 1 up to person 10, and I do not only measure or register, ask the height in centimeters for the persons, I also register, measure, ask the weight. So now I have two measurements. I have two columns in my Excel sheet, the height and the weight, right? Then the so-called scatter plot that I'd show you here would be a nice standard way of showing the data, looking at the data. Where we could choose either way, but let's choose this way. It makes slightly more sense, I find. Let's see the weight as a function plotted versus the height, right? And I think the numbers here, we have a mean height for these data of 178 centimeters. We have a mean weight of 78 kilograms. I've just indicated the means of X and Y in my plot. Then I see my 10 persons here. And what's the story of these data? Right? I think most of us would have concluded that all the way back, maybe not third, but fifth grade. This is the story, right? Number-wise. Expressing what we could have expected was we used a little bit of brain activity. We would probably expect that at least on average higher people tend to weigh more. So it's not a too surprising fact of numbers that hits me here, right? I'm looking at the numbers. They tell me taller people on average weigh more. I also see that it's not like the dependence of the weight on the height, of course, is not a one-to-one thing, right? It's not like we know exactly the weight of a guy who is 190 centimeters by looking at numbers. Of course, we have natural biological variability. All of us being the same height, we do not have the same weight. How can we quantify both of some of these things? Well, here's one way. There is a way to quantify this story of those two things, the height and the weight, that they vary together. They co-vary. When one is high, the other seems also to be high. That is co-variation, right? One varies to the right, the other varies to the right. We can quantify co-variation by something that looks a little bit like our variability measure, but then again slightly different. The difference is we take X differences and multiply by Y differences. So we combine the two differences. We don't square one of them and add them up like we do in the variance. We combine the two. And if you think about it a little bit, let's just think. No, I actually have a nice slide showing it. Then I'll show you the other formula in a sec. If you think of it, here I just made it very explicitly. Where I looked at, I'd like to actually show you, sorry for jumping, but I'd like to show you the plot here. These four guys down here, they are both low on the height and the weight, right? Which means that they have negative differences, both on the height and the weight. These guys up here all have positive differences, both on height and weight, right? So their difference to the mean is positive, their difference both on height and weight. So when I multiply positive, positive, it becomes positive. When I multiply negative, negative, it becomes positive. So all of these contributions to this so-called covariation that I'm showing you here, I'm showing you these differences, minus, 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 plus, 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 blah, blah, and so forth. All of these contributions then become positive, and this is by no means a proof of anything. I'm just doing a heuristical argument in letting you hopefully share the insight. When I see this definition of what is called covariance, I can have a gut feeling that it makes some sense, that when it gives me a positive number, it tells me that I have a positive trend in my plot like this. This measures a positive relation between the two things called covariance. Now this is something that depends on the scale of x and y. There is a scale-less number expressing a similar thing called a correlation coefficient. The correlation coefficient does the same thing, but with one more thing, that it is being standardized by the standard deviation of the x and the standard deviation of y. I just defined those to you 5 minutes ago, right? Compute the standard deviation of the heights, compute the standard deviation of the weights, use them in the covariance, combined with the covariance formula. It can be shown like this, or it can be shown like the formula like that. Having defined this number, this is called the correlation, the sample correlation coefficient. This is a nice number. For our data, let's just look at it. For our data, it became 0.97. So the 10 numbers I showed you would provide a correlation coefficient of 0.97. Let me show you this one and then get back to my summary points. This is how two things that have a correlation of 0.95 looks. This is how two things having a correlation of minus 0.5 looks. Slightly negative, but also a lot of noise, you could say. It's not a one-to-one thing. There's definitely an average relationship, for sure, if I looked at that, but with a lot of variability, of course. This one is the zero case, completely flat. This one is another zero case, which makes us think that the world is not as simple. The world could be more complex than the correlation coefficient can even comprehend in a way. Because maybe the world is not linear. Many real things that will hit you in real life, physics, chemistry, material science, whatever kind of engineer you're going to be, real life phenomena will very often be nonlinear. However, it's good to have a linear place to start sometimes. The correlation coefficient measures the degree of linear relationship between two things. And if it appears that two things are perfectly related in this quadratic way, the correlation coefficient itself would never realize. Which is telling us that the correlation coefficient is not the one and only tool for the rest of our lives for everything. It's nice to quantify linear relationships, but when we use it in practice, we should always look at the data also, because it may be completely irrelevant to know that the correlation is zero, because we need to know this nice curved relationship. It's more complex than the linear story. So, that's correlation. And to summarize, before I should have changed those two plots. This correlation coefficient will always be between -1 and 1. I've shown you different patterns that corresponds to different values. Measures linear relationship. It becomes only plus and minus 1 mathematically when the points are exactly on the line. It becomes positive if the general trend is positive. Now in my example, I only had pure terms, right? But it wouldn't change the positiveness that we had a few being slightly negative, actually. It will be negative when the general trend in the data, the scatter plot, is negative, right? Positive correlation, negative correlation. Nice way to tell the story about how two things are related to each other. So combine the plot with the correlation coefficient. That's very typically done. We're going to get back later in the course to the statistics related to linear regression and things like that, which is an important topic. But for now, we just look at the data and compute a correlation coefficient to summarize the story. That was actually the summary statistics story that you should now start practicing. So we'd move to the last